Hello, I'm Xianghao Zhan.
And I'm Yiheng.
Today it's our great pleasure to introduce our project to you, Fast Brain Strain Evaluation in Head Impact. The background of our project lies in mild traumatic brain injury, the MTBI. This type of brain injury is very common in our life, such as in bike accident, falls from stairs, and many contact sports such as football. Because most of MTBI is subconcussive, if we could better monitor brain deformation in head impact, we could better prevent damage accumulation and give early warnings. Conventional method to characterize brain deformation in head impact is FEA, the finite element analysis. It requires complicated computational models and takes about 30 minutes to calculate the brain strain for one impact. Therefore, we are motivated to apply deep learning to better characterize brain strain in a much faster manner. The input data we use are the kinematic signals recorded in 596 impacts from mixed martial arts and American football. They are recorded by Stanford Instrumented Mouth Guard. The output labels are the maximal principal strain, the MPS, calculated by the KTH model, and it is a widely used FEA model. We firstly padded the MMA and football signals with different lengths to be of 20 to 100 milliseconds and aligned the peak to be at 100 milliseconds. Secondly, we reduce the dimensionality with PCA learned from training set. Then we need to predict 10 principal components and reconstruct the over 4,000 final output. Additionally, to make comparisons, we also extracted features from the signals, including the maximum values, integral values, etc., to build DNN models.
We have built 4 types of models for 2 main tasks: DNN with engineered features, DNN with padded signals, DNN with PCA and padded signals, and finally, LSTM with PCA and padded signals. Firstly, we regard the brain as a single entity and try to learn to predict the 95th percentile of MPS to characterize the whole brain deformation. We repeated the process for 50 times with random datasets lit and parameter initialization. Here, our best results come from DNN with engineered features. The architecture is shown here. This model reaches an R-square of around 85%, which is better than most of the models in a published article. Secondly, we learned to predict the strain of every brain element. We've used data augmentation, dropout, altitude regularization, atom optimizer with learning rate decay, and optimized many of the hyperparameters through the experiment and validation set. Meanwhile, we have also modified loss function in LSTM with PCA according to the different explained variants of the PC. Finally, we compared the models. According to mean absolute error and root mean square error, the best models are DNN PCA with padded signals and DNN with engineered features. Here we show one example prediction ground truth plot and error histogram. The accuracy of deep learning methods were further justified in visualized results after we register the brain elements to spatial points. To sum up, in this project, we applied deep learning to brain strain evaluation. Our single metric model works better than most models in published articles, and our novel element-wise model could give brain strain similar to KTH model, but in over 3,500 times much faster manner. That is all of our presentation. Thanks for the privilege of your time.